All right. Hi guys. This is Hudson, and we're gonna be doing some stuff today uh about yeah, whatever you want to do, man. But yeah, no, we'll be continuing from where we left off. Oh, not no. Today I plan to do some other stuff, talk about some other type of rambling. Um, more about like uh uh I just plan to like do videos about like um we're gonna be seeing more about the DP state space traversal. I think we ended at something. We ended looking at a specific way of doing DP state space traversal. And today I will show you there's a problem with that. There's a problem with the state space traversal I was talking about. And today particularly we're going to be looking at that with a problem called two city scheduling. It's a legal problem, and I'll be going through some stuff about the regular state space traversal, right? So you have some question, and the question tells you to find maximum, minimum, and or like find what some value you can get, and then sort of like give us the value, and uh and then all you do is you define a bunch of state one, state two, state three, and then you sort of like recurse through the various states. Now, bear in mind that whenever you have a decision tree, you have this, and a decision tree keeps splitting at like different points. This is how you read it. Um, this is this or this, but it's this and this. So this and this. So when they're split into two parts, they're or. But when they're, like this and this and this and this and this. So this essentially means that when you have a recursion, well, what does this mean? Okay, so say you have you wake up in the morning, which is this point. You go to school or you go to work, and then you eat and you read. You eat and you read. Now, if you actually want to see all the possible ways, right? It's you go to school and you eat, or you go to school and you read, right? Which is this part of this tree right here. You read, or you go to school and you eat. You go to school and you read. So when they're all on the same line, you're reading. Now, I don't know how does this relate to recursion, like this recursion? Um, well, I mainly brought this example up to kind of show you that when you have a bunch of states, let's see if my argument holds. So you have state one, and then you have state two, and then you start from this, and then you go to uh certain let's just say state I, state J, and then state I also splits out into a bunch of parts, and then you have state I plus one, state I plus two, and then state J also splits out into state J plus one, and state j plus 2. If you wanted to find, say, all the methods, right? How many traversals you're doing? Well, this comes down to something like you're doing state 1 and you know and this state 1 and this, or state I and state I plus 1, state state I um or state I plus 2. So this state and this plus this state and this, right? So this state and this plus this state and this. Essentially, let's write it down. So all movement comes state 1, right? So this is actually state I and state I plus 1, or state I plus 2, plus you go to stage J or state, whatever you go, and then it's and state J plus 1, or state J plus 2. This is all the traversals you're kind of doing. And what was I even about to say here? Okay. Actually, this is a not so good example. Let me use a simple example. You have I and J. And you can either increment I or increment J, right? So you go down to I plus 1 J, right? Or you go to I J plus 1. And then you go here. Then you go to I plus 2 J, right? Or you can go to I plus 1, comma, J plus 1. And then over here you have I plus, either you go to I plus 1, J plus 1, or I J plus 2. And you're sort of asking a question, well, what are we doing? Like how many traversals are we actually doing? Well, let's see, let's calculate. So what we're doing here is essentially this becomes an OR operation. So you have I plus 1 comma J, that would multiply I plus 2 comma J, or I plus 1 J plus 1, right? Plus the second path is you have I J plus 1, and that multiplies I plus 1 J plus 1 plus I J plus 2. So this is all the traversal you're doing, right? This is all the traversal you're doing. This is I plus 1 J plus 1. And I think if you were to sort of like expand it out, you would notice that you're doing something like, I'm pretty sure you'd find it would be I times J, essentially. You'd visit all the states of I times all the states of J. And so that will essentially be your complexity. The complexity, whenever you're adding states and you're moving through the states like this, you move through all the states of I. So I plus 1, I plus 2, dot, 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 times j plus 1, j plus 2, dot, dot. This is essentially what you're doing, right? And that's why you can see from here, you can see I plus 1, j multiplied by all the variations. So you have I plus 2, I plus 1, j plus 1. You'd get I multiplying, you'd get a state where I, and then all the changes of j, I plus 1, all the changes of j, I plus 2, all the changes of j. And so what I'm claiming is that whenever you add multiple states, so if you have A, B, C, and then there's different states of A, your complexity for this thing right here becomes A, right? A plus 1, A plus 2. And let's change the color. And then B plus 1, B plus 2, dot, dot. And then let's change the color. And then C plus 1, dot, dot, dot. This is your entire complexity. And this is why you're gonna get a case of this. So you will get the case where you have an A plus 1, you know, B plus 1, C plus 1. Because especially if you were to expand this out, this would cover all the ranges of this plus. It'll be like, what is it called? It's some kind of polynomial expansion, right? You could cover all cases. And so if you have a grid, that's why if you're traversing, you can have a grid of M, N, right? And you can traverse it. You essentially your complexity will be M, N. And this is also why if you have an array 0, 1, 2, 3, and then you're saying that well, position, right? You're gonna go to each position. Let's see what state will classify this. Okay, so you're gonna go to position I and have a decision, right? You have a decision. You have a decision. Either take that or don't take that. That this, the complexity of this is you're gonna have, for this one, for example, you're gonna have positions I 0 and 1 and 2 and 3. And your decision is gonna be 0, 1. Right? And so if you were to multiply this out, you're gonna get if you want to multiply this, instead of using 0 and 1, let's use something else. Let's say true and false, so that our expansion makes a lot of sense. And what I mean by this is that you're gonna have so if you took this, you multiply this by all the stages of this, you're gonna have t times 0 plus t how do you even write this? Essentially, yeah, you're gonna get t0 t times 1 plus t times 2 plus t times 3. So you expand this out. Now this whole thing is multiplied by I see. No, this is a bad example. This is a bad example. Doesn't scale. Doesn't scale. Does not scale. Example does not scale. I have to sit down and probably come up with better examples. But my point is, you get what I mean? Like you need to be careful when essentially if you're doing recursion, you're going to go through all the states. And so your complexity will be all the states of A times all the states of B. So why does this matter? Well, this matters when you have very large states. So, for example, if you have some numbers, right? State your state is A, B, C. And then A can have like 100 different possible variations, and then B is something like a value, and then that can go as high as say 10 to the power 4, and then this can has a few like 1,000 different variations, which is 1,000. You don't realize, but bro, this immediately goes to what is this 10 to the power 6 times 10 to the power 3, which is 10 to the power 9. So this becomes very large. This state becomes very massive very quick. And there's no way, well, there's no way that you can store this much stuff. You're gonna TLE. Most if even in a map. I mean, what's so the time complexity for a log of insertion and deleting in a map is log of n or something, right? What's log of I don't know if it's 10, if it's log 10. I don't think it's log 10 because it's a binary tree. But you do realize, that most platforms will not support log 10 to the power 9 different states. That's just way too big. But if you found a way to reduce the state, to take this state out, you immediately get A, B, and you get something like 100 times 10 to the power 4, which is 10 to the power 6. That's still quite large. Most states won't, most judges like legal or whatever won't allow you to store 10 to the power 10 to the power 6 states. I'm not too sure. I don't think most things will allow you to store such a large base of states, but we'll see about that. Um, and this is like, I'm gonna go through like some in-depth methods of yeah. Okay. I'm gonna go through some in-depth methods of like different state traversals and why some of them are just ridiculous. They're not possible and they're not practical. And you shouldn't do them. Let's see. Oh no, I wanted to get the lasso. Yes. What did I say? Oh, that's sad. Let's clean this up. Let's clean, 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 clean. This is why, it's one of the downsides of having a lot of space to draw. Because now you have to clean up, everybody clean up. And this should not be in a video. But since this is a rambling, it's not necessarily supposed to be cute. So I can post whatever I want, whenever I want. I suppose I should probably Okay, let's see some stuff again. Let's see. Let's bring the leak code question I'm talking about. I saw it, I had in mind, and let me show you something. Okay, I'm back. Multi-bono. Okay. So the question is called two-city scheduling, right? It's a leak code question. Oh, sorry. It's a leak code question. The question says, oh, this is the wrong question. Wow, is it really? Oh, two. Okay. Come on, Nico, don't do me like that. This is the question. Two-city scheduling, right? The question goes like you have a you have so this question is kind of weirdly written. I don't know why they cannot be specific, right? And they keep joking around, and then we have we fuck up, and it's like be specific. It's really badly written. It's not that great, right? But let me just try to explain. You can check it out on your own. It says you have a bunch of costs, and you have uh a bunch of people, right? So the cost the 0, 1, 2, 3 represent they represent the cost of taking a person to either CDA or CDB. No. So it's the cost of either taking a person to CDA or CDB. And so you can take a person to either CDA. So for let's say 0, 1, 2. So the cost of taking person 0 to CDA, right? Is 10. Cost of taking person 0 CDB is equal to 20. Right? And so it's the same thing for and you can take, and then they're saying finishes such that at the end of the day you have n over 2 people at CDA and n over 2 people at CDB, right? So that's what you have. You have n over 2 options for CDA and then there's 2 options for CDB. You can also see this as some kind of like 2 different lists, right? So cost for CDA is 10, 30, 400, and 30. And CDB is 20, 200, 400, 20. This is a mistake. 200 should be 50, I believe. Okay. And at any point in time, so at any point in time, you have to either choose to send person A to CDA or to CDB. And at the end of the day, you have to send exactly two people. Sorry, n over two people to city A and n over two people to city B. To generalize this, I mean, if you were to add a third state and say, or don't send any person to city A or city B at all, um, and so you're like, okay, either I send person one to city A, city B, or I don't send person A to like any city at all, right? So I don't choose person A. That could be a kind of a question that could just hit you, or these could be a bunch of other cities. D, city E could have say 9, 10, 20, 30. CD and CDD can have 15, 8, 8, 7, 6. So at the end of the day, you have to send a number of people to city A and a number of people to city B. The number happens to be n over 2. Now, generally, um this is kind of called optimal allocation, right? I think whatever for every person, for every index, you have to choose to send a person to one of these places, either A or B or C or D. But at the end of the day, do it in such a way that you have the minimum cost. Um, in such a way that you have a minimum cost. So we'll sort of like tend to we will try to see if we can reason about a general case. But now we're just going to reason about the case where you have two cities, A and B. And there's a greedy approach to this. The greedy approach is sort of like find some kind of way of defining, of seeing if it's better to send person A or city B is person B, person 0 to city A or to city B. You can sort of like come up with a greedy algorithm for this. I came up with one. It didn't work. My greedy algorithm was to divide it and find what 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 city had the best cost or something like that. I'm not going to talk about the greedy. You can see that on LeetCode. Everybody does a greedy on LeetCode. Um, and I also think that actually you should learn the greedy. It's very important. But in this video, I just want to go over some of the state traversal methods in this. So, in a question like this, you want to ask yourself, how do I move through this, right? Such that I can get the minimum cost, or maybe it was the maximum cost. It doesn't really matter. But we want to find the minimum cost in this question, and then you're like, okay, well, what's a node in this? Um, and if you look at this, you normally want to have really broad nodes, right? So you can move through very easily in the beginning. So you can say that, okay, position for sure and very necessary because most of these questions are sequential staged selection. So you're going from 0 to 1 to 2 to 3. So position or index, but let's just call it position. It's very important. Keep track of. And then you're like, your decision. I have to send the person to city A or city B, right? So decision is also very important. I guess and now each decision has a limit. And so um you have a bunch of decision limits. And so you have the limit of decision A and the limit of decision B because you don't have infinite choices, right? You have to choose specific amount of people to send A, and if you pass that, you shouldn't be able to go forward. You shouldn't be able to send more than n over 2 people to city A, and so you have a limit state to bound that. It's very important. And what else? And the value, which is what we're minimizing, right? And so you have this long ass states to keep track of. The position, the limit of A or B, decision, which is either to go to A or B, and then the value. And so if you use what we did before, let's see. So we're writing something like we're like, and this is just pure state recursion traversal, whatever. You know what I mean? So assuming that you have this thing, right? It's let's see if we can just steal this. Let's see if we can steal and put it right here. Okay. So our node, this is really packing, but this is 0, this is 1, this is 2, this is 3. And so there's two ways you can do this. You can do this as like, so let me show you. You can do this as you're leaving. Initially, you can start from a begin position, a begin state. That begin state. So you can start from a begin state where you're positioned, I don't know, say -1, and you can your decision is either go to A, right? And then the limit of A is you haven't chosen anything. So the limit of A is still the limit of A, and the limit of B is still the limit of B. You have 0. And so this means that we're from that state we're going to A, or we haven't made any decisions yet. And so from this starting state, we we can start from this starting state. But I usually like to go to the state and pick whatever I'm getting. And so as opposed to computing what we have when we're leaving the state, I go to the state and pick up what I want, right? So for example, someone will start from a starting state. I will start directly with 2 states. The first state I will start with is you're already at position 0, and you made a decision to go to A. So you've picked up A, and now the limit of A is you now have 1 because you've picked up 1 item from A. The limit of B is still 0 because you haven't picked up anything from B. And then the value is 10. And you have you go to 0, right? Position 0, which is this, but then you choose to take item B. And so your limit of A, your decision is wait, let me change the name. Let me call it the DA so it's not confusing. So you have decision is A, and over here decision is B, right? And then the number of A is 0 because the limit essentially refers to the number of each of the objects picked. Number of B is 1 because you just went to that state to pick B. And now the value will be whatever you have plus the cost of that decision, which is at this point 20. So let's, this is actually works. This actually works. I can code this up real quick and show you that this actually works. However, this is too big. But let's assume that we don't know that, and we just want to try this this out, right? So code. Let me name it to city, but recur because it's recursion, not CPP. And alrighty. So this is it. So we have something like int main while. We can use a while for recursion, or we can use a function, but let's use a function. Let's go to function a DFS, right? Let's avoid DFS. DFS. And let's see how many states we're gonna take. So our states would be int position, int that's decision, it's just D, and an integer represented the num of A, and an integer representing the num of the and our value so far, which also happens to be an integer, which is the value. Let's just call it val. Can you go somewhere else, little sir? But let's not make it caps. Now, first of all, we have to decide what's our base case, what's our boundary. Where do we hit and we're like, all right, man, this is not good. And I like to write it as a function so you can think about it, because if you just, it's very important. Not knowing where your base cases or your boundaries are really can absolutely destroy the code, make you do an endless loop. So always remember to write it as a function on its own. So you can ask it, have I hit any boundaries? And if I have, get out. So one boundary would be that, let's go back to this. One boundary would certainly be if we went out of position, right? If we went out of position, well, then we're not picking anything. If we suddenly came here, we can't decide anything. So if position is greater, right, than the size, that's one boundary position. Another boundary position are these limits. There are limits for a reason. So if our limit, right, if our limits, if we hit our limits, right, and so if we hit our limits, we can't do anything again. All right, if you hit our limits are definitely boundaries. And but say if I were to increase my limit, right? If I were to try to go into, say, position 0 and I choose A and I do lim plus 1, but then the limit is this, and then B is still in limit. Is it does it qualify? Well, no, because lim plus 1 is an out of bounds limit. And so immediately we cannot go to such a boundary. We can't exceed it. So our limits always have to be in bounds. It has to be bounded checks. So I guess let me see if I can sort of what did I choose? Oh, what alive, what alive. So in order to decide what the boundaries are, we need to have a test case, right? And that's going to test sample. Well, let's take one. Copy it. No, this is too big. This is too big a test case. And I need to use using namespace STD. It's not too much of a great practice, but I'm not gonna be the type of dude to get errors, STD errors, in like a demonstration code like this. Nah. Uh, um. So to check our boundaries, we need to first of all we need to pass everything we have. There's something in C that's called perfect forwarding. I think you can do some perfect forwarding here. Actually, it's not even relevant because all we're doing is primitives. I think the rule is primitives by value, objects by reference, something like that. And so we pass all the values we have to this function. And we have to return that our position is less than, this. We don't need to do anything with D, so we can take that out. Actually, it shouldn't even be int. Let's make our decision bool because it's two choices. Because a bool is smaller than an int. Our limit of A is not so we're going to go by negative boundary check. We're going to say our limit of A is not greater than what it's supposed to be. Limit of B is not greater than what it's supposed to be. And the value, yeah, we don't need to inflict the limits on boundaries on the values. And so by doing this, we already know that oh, we don't know anything. It's okay. So we have to return that. Let's a test case called this has to be a vector or a vector, right? I think there has to be like what is it? How do I move sideways? Select the cost. Um, is it go to we can just use this. Compiler will help us here. 10, 20, 3200, 3200. I think it's 150. 50, 30, 20. Yes, yes, this is it. So after doing something like this, I guess what we can say is what next? Well, we have to because now we have a cost, we can store the limits, right? We can also store the limit of what the limit of A is. It makes our life a bit easier. So we're not writing equations in our boundary checking. That can be like kind of annoying. So currently our limits is that, lim of uh and limit of A is equal to costs dot size over 2, right? And that's the same thing as cost as limit of B. We'll write it either way. Limit of A and limit of B. Right. you have to make sure that our position is less than costs size, right? So this will mean that our position, this is right, Our position is less than cost of, right? Our limit is less than this, and our limits are less than um and our number of A. So we can send exactly, so it has to be a number of A is less than or equal to, right? Because it can be either less than or equal to two people. Whenever, because that's not zero indexed. So number of A is less than or equal. Sorry for the dogs, man. I don't even have dogs. Goddamn. Limit of A. And our number of A and the number of B is less than or equal to limit of B. Yeah, I think this should work. We'll test it out, just to ensure the code is working fine. 0. I'm going to check that our bounds something like this. Assuming okay, position is 0, we go into position 2, position 3, and in this case, since it's 4 items, we cannot. Let's see if we try to take more than the limit. And so you take three people in A, then B is 1. This should generally return not bad or like not good or whatever. G++. What now? Why do I keep doing this? Really not. Says no, yes, it says it's bad, right? Because we cannot take more than 3 items of A. But if we, if this was 2, we can do this because we can take 2 items of 2 and then take like an item of 1. So it says yes, this is a possible. Oh, you can't see it. It says yes right here. 1. Alrighty. So how would our DFS movement go by? Let's see first before we start deciding to cache states, right? That's all our method is at the moment. Location states. So we'll get to a point we're gonna ask if you're in bounds, return else. Decision is either send the person to A, send a person to B. Okay. So we're gonna say, if you're at this position, let's write let's say bounds check, right? So we've checked the bounds. This is a valid position. So if you're in a valid position, now what can you do? You can do some DFS and let's okay. So since A is 0, send to B is 1, right? Or DFS. So so you'd be going to position +1. This is not what happens when you do copy and paste. And then, since we're going to A, I already defined a preprocessor directive on the top here that just sends to A. So you first of all, you go to A, and then since you're going to A, your number of selection of A goes plus one, and the value plus costs. So cost of the new position was plus one. And if we're choosing A, the value would be 0, right? So the new state of the value of the new state we're going into will be this. So we can go into this state, and then after that we go into this next state, and then next position we're gonna do a send to B. And then because you chosen B, your number of A stays the same, but then your number of B increases, right? Plus one. And your costs is now the value you had, which is this is the next value we have, right? Okay. Now, what's the bound check? Is there any way that, this algorithm will keep on going on and going on and going on and never stop? Oh, it should stop immediately it hits a bound, right? So we're going to say if bounds, base case or boundary or whatever, boundary case or whatever, of this new position, number A, number B, number B, right? If it's not in boundary, you return, right? So first of all, I will show you this. And what I will say is that if you look at this very carefully, you see that this is how the DFS will work. It looks quite simple, quite easy, fun stuff, not too crazy. But that's exactly what recursion is. So they trick you to make you seem like it's fun and easy, and then you hit some cases. It's like it's not working. Well, sure, of course. If our if our state is a valid state, though, we will print out the state. I'm going to print out the position. We're going to print out the number of A. Number of A. Going to print out the number of B. We need to print out our decision. No, we don't need to for debugging cases. I don't think I just want to show you something. Position number of A, and then print out the value. So so this will be position. number A, number B, position, number A, number B, and then value, right? You should compile fairly well. Let me check the code one more time. I hate it when the compiler is screaming. However, know the boundary will return. As effectively use pin out of tape. And then we go to the next stage, we pick A, it increases, blah blah blah. Position. Or we go to the next position and pick B. Okay. We're gonna be something like there's no way even after this. Bound. You see? Okay, that's let's leave that out. Okay, I think our position our function works. So now we will call our function, which is dfs. And we're gonna call it in position 0. Okay. We're gonna do a send to A. Um, if we send to A, the number of A increases by 1, number of B increases by 0, and then value is you know, that's the downside of what I do. I don't have an entry position. I just immediately declare two states, two visible states, like the first two states or whatever states. Position 0. And to B, this number of B is by 1. We go to cost of 0, 1. Nice. Ocho Cinco. Okay, so since we have segfaulting, see, we're breaking it, we're hitting certain positions. Oh, it looks like we're going out of scope. Looks like we're going out of scope. How is our position checking? Return that so it looks like we don't check if that position's we have to check if because we call this right, we're like, okay, but if you call boundaries position +1, position +1, yeah, no, that should how are we going out of bounds? I don't get it. Oh, I see. You see, this is the problem with boundary checking. Right, this is a problem with boundary checking. Okay, we're gonna check some more boundaries. We're gonna check some boundaries before we even before we go here, we will check some boundaries. Because what's going on is that see how I'm accessing the cost position +1. If you get to 3 and I'm trying to require position +1, you see that's a problem. So that's one of the problems. That's why. Okay, I know what I'll do. And so I'm gonna do this. copy, and say that if this is the case, position +1, and then NA +1. Then let's do this. Right? So that I'm not like doing this prematurely, this P of S +1. That's hidden. This is why I hate using vectors. You access some kind of space and it's not there, this compiler will scream at you. Even though you actually won't use, like over here, I'm not gonna use it. I'm never gonna use it if it's not in boundary, because immediately it hits the boundary, it it fires back. But because I'm already accessing it. So it's the same thing for this. So boundary, what boundary was I checking? Over here, I'm like, if boundary position +1. So I should also do the same thing over here. Copy. So if boundary position +1, +1, and we call this. Right. Now, in this case, now it's better because we're not, if this bond fails, right? If position +1 is not, it won't even evaluate this thing right here. So we can do some clear, compile this. Let's say that out. Now, what's the problem? Well, now it's just going through all the states. The question asks is for the minimum state of where you sent two to this state, two to A to town A and two to town B. And if we were to see all of that, the minimum is this. It's 110, and so we're gonna take that. However, because this is sort of like this is regular recursion, right? So we're going through all the states. Um Now one question is, are we doing more? Are we hitting the same state twice? Right? Are we hitting the same state twice? Let's see. Do we have any state that competes twice? See, when you have a state that can be as large as value, that's when the recursion becomes a problem because you won't be memoizing enough states, right? Because the idea is if you've hit a certain state before, you shouldn't. So let me show you what I'm talking about. If you've hit a certain state before, if you hit, say, 0, DFA, 1, 0, and 10. If you've hit this before, you know you're gonna go down the same route, right? And so there's no need to do this again. And so what we can do is we can say, okay, let's store some states. And then, so now let's see something. Let's try to store some states. And then we'll see if we've seen a state before. If we've seen a state before, we won't go to this state. Um, if we've seen that state before, uh, I don't think this will help doing that simply because if we look at the problem, our state value, right? Our state value is a function of the length of how big value can become is the length of the array the cost array times the value of each. So the worst case scenario is if every single one is 1,000 and the length is 100. And so we're choosing 50. 50 times 1,000. 50 times 1,000. Okay, so let's see how big this is. So what is the time complexity of what we just cooked up? Okay. So the time complexity of what we just cooked up is you have this. So it's what is this? Position, right? We know that position is max what? It's max in the question it says 100. So that's n times. Now the decision is only 2 times the number of A and number of B is n over 2 respectfully, right? The n over 2 times n over 2. And our value, how can we define our value in terms of our value is max gonna be 1,000 times what is it, like 100? 100. 1, 2, 3, 4, 5, right? So it's 100,000. Or is it? It's 1,000 times 100. It's 10 to the power 3, 10 to the power 2. Yeah, it's a 10 to the power 2. Is this right? Yes, this is right. This is sorry, 10 to the power 1, 2, 3, 5. So the complexity for this algorithm we just cooked up right here is n cubed over 2 times 10 to the power 5. Now, we're told that n can be as big as 100. So 100 cubed is 100 10 to the power 2 to the power 3 10 to the power 5. So this time this is power 5 times 10 to the power 5, which is 10 to the power 10. That's too big. Oh, sorry about that. Who was calling me? Our algorithm becomes essentially like an n cubed. And 10 to the power 10 to the power 5. It's not some like simple number that we can just say it's a constant. No, this is quite massive. 10 to the power 5. So if the thing is 10 to the power 5 times 10 times n cubed over 2. That's quite big. That's very big. You know, our algorithm, we already calculated, it blows up to 10 to the power 10 over 2. There's no way leak code is going to let us do this. There's no way leak code is going to let us do this. Is there a way we can hack this? I don't know. I mean, I've never really tried to hack this. I think what we probably can do is if we so we're doing probably around this many function calls, right? We're gonna blow up the stack. You have to realize the stack is an actual data structure. You're gonna blow up the stack. This will blow up the stack. But let's see if we can submit this. But no, before that, let's try different examples. And so when we try this, we can see that State where we've chosen 2 and 2 is 110. That's the lowest we can get, right? Because we have other states where we've chosen 2 and 2, like this one, where we've chosen 2 to A, 2 to B. Um, and the value is like 630. 110 isn't right, it's too big. Um, and it's like how do we write this in such a way that we can write this functionally and store, the function values, but if we have like states, how do we like store the states, right? Well, for starters, it looks like we're blowing up our stack by doing, a lot of function calls. And there really is no way we don't have we can't see the size of our stack. So we can't see how many function calls we're doing. But let's try to see something. You have 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? 18. And we had n is 1, 2, 3, 4. What's 4 cubed? I don't know. 4 cubed 64. Cube 64. Yeah, but our complexity is something around this. And we can all agree that this is too large, right? It's n cubed. We're gonna go through this many states. And yeah, that's too big. That's too big. Sometimes recursion works. If you can just find a way to reduce the states, that's what it comes down to. If you can find a way to reduce the number of states you're visiting, optimize out the states, right? If you can optimize out the states, you can do a simple graph, traversal, and you will be fine. Most of the time, people don't want to go through the pain of, until they stick with leak codes, like, or whatever judge they're using, convention of like, oh, this is the solution. But, I'm like to get out of the box and think about these things. So let's see. So our algorithm essentially has a position, our decision, our limit of A, limit of B. Is that it? And our value. Our value we've already established can go as big as 10 to the power 5. You have to find a way to deal to not do this many, not do this many states. 10 to the power 5 states is too big. I think ideally if we're around if we were to we had this times this times this 2 and cubed. I mean, we can sort of push the algorithm to n cubed. I think you can even do more optimization and optimize out. Yeah, you can even do more optimization. Optimize out the position, and then you'd be doing like, I think it's somewhere around like n square. But you have to realize that every level of optimization, it gets harder and harder because the number of things you're keeping track of is derivative. You're deriving this or that. Well, assume we weren't keeping track of value, right? We took out the value and we just kept track of the position. Our decision is just 2, so it doesn't have a lot of stake. You know, it's either we'd go to A or we go to B. It doesn't really matter. And but yeah, let's try to blow it up. Let's see what happens if we, you know, we use an even bigger test case. I stole some test cases from the code. Now this is gonna make my PC hot, real hot, because it will really blow up. Now look at that. Will you look at that? Let's see. The solution is when we've sent this is 1, 2, 3, 4, 5, 6, 7, 8. So I think where we sent 0, 1, 4, 4. Where we sent 4 to A, 4 to B. So for example, this might be a solution. This might be a solution. Let's see what the code say the solution is for this one. 515. Is that what I'm using? Yes, I'm using that one. And the solution is 3068. 3086. See. This is too much. I can't look through all of them, but the solution is somewhere around here. Yes, that's it. That's the solution right here. 3086. Lucky number. Now, is there a way we can hack this? We can still do, state traversal and still let's do something. Let's try to store the states, and if we see a state we've seen before, we shout it out and see if we're even like hidden multiple states. They create a set. Set will have a tuple of what are we storing? We're storing this, right? We're storing this. So int okay, actually this is bool. Int bool int so int bool int it's gonna be funny. Let's call this states. So okay, and let's do something with this. So instead of just print it out, we say that if state, right, count position and decision and number of A and
and number of B and value. So if we've seen this before, we say cout state seen before. We just want to see if we're hitting the same states again. That's just all we want to see. If you say states seen the same before, else, we're going to say state copy dot insert right, 1 2 3 4 5, 1 2 3 4 5, and then in the beginning we're going to insert this two states. So states, is it state or states? What did I name it? Named it states. What do you mean state? Dot insert, and we're gonna insert this. We're gonna insert this, and we're gonna insert this too. Okay. Now we're gonna see if we're even hitting, certain states multiple times. Else if, where am I using an else if? I never plan on using an else if. Oh man. So you telling me we hit only two states we've seen before? That's ridiculous. That is ridiculous. Am I doing something wrong here? What? Okay, let me. So we print out, whole lot of states, but we also print out. So around here, we hit a state that we've seen before. You see how ridiculous it is? This is how bad it is. This is how bad our memorization is, We see only two states. We're able to memorize only two states. After that, we don't hit any state we've seen before. I wonder why. I wonder, oh, and even that is probably our first two states. If we hit our first, if we insert this and insert that, and we call DFS on the first day, check state hit seen before. Yes, it looks like only our two state that we've seen. Everything else is fresh, and so our value is so big, and it's changing by one, by one, by one, by one, that there's almost no way that our value can be memorized. it seems like the value is making this in such a way that we're not getting any overlapping values. Because every time we're incremented by something, I don't know why it looks like, yeah, our values are not they're not overlapping. That's not good. That's not so good. That's quite bad. That's quite bad. You know? That's really bad. Let's do this clear. Let's only two states we've seen before. Those are our beginning states. Let's see something. Now let's do something. Let's do this. Let's copy this. And let's post it. Okay. Let's see if we hit any, pre before seen values. Looks like we're not hitting any other states again, bro. Like it looks like our value is so large that what's happening is that we're computing newer values every time. Every time we have a new value, every time. Every time. And this is gonna run us out. It's gonna run us out. It's absolutely gonna run us out. I don't think this will work. I don't even think LeetCode is gonna accept it. I mean, it's 10 to the power. Can we express our value in terms of n and see if LeetCode will accept it? So our value tends to be, so it says, and our value can be as big as each one. Value can be, the biggest value we can get is if we have n over 2 times 1,000, because it means we're taking n over 2,000, right? So n over 2 times 1,000. So in terms of the raw complexity, let's see, raw complexity. We have this is n times decision to 2. Doesn't really matter. This is n over 2. This is n over 2. Now value can be as much as can be as big as 1,000 times n over 2. So let's see. So our value can be n to the power 4 or 2 times 1,000. Approximately, because it's 500 times n to the power 4. Is that too big for us? I mean, will LeetCode accept this? I don't know. I do think LeetCode will accept this, but frankly, you know, I think our positions can be only as big as our position is like only 100. Right? The maximum positions we can have is 100 pairs of the question. So it doesn't even make sense using that. Maximum the length of the thing is 100. So complexity is, assuming we implemented this as a constant, right?
as its constant. So it's 100 times, which D, which is 2. So even this is 200 times. This is n over 2, n over 2, n over 2 times n over 2 times 1,000 times n over 2, which is 500. And so it becomes 200 times 500 is 2, 5, 10, 10,000 and cubed. 10,000 and cubed. Treating 10,000 like it's a regular constant is funny as hell, bro. 10,000 is big enough that it can have an impact. Because, yes, 10,000 is big enough. Do I actually have an It's not some constant, 10,000 is quite big. So we can't just dissolve our positions into, just claim that, oh, it's just. However, I still get a feeling that Lee Code will accept this. I know what I'll do. Let me do something. How about we submit it and we see something? No, 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 no. Um, if I try to, you know, okay, we're gonna blow this thing up, bro. We're absolutely gonna blow it up. We're gonna be doing about okay, so I'm gonna try loading my solution. And I'll see. Oh, but you can't see it, okay. Okay. This is I did the greedy method and it was not cool. I mean it worked, but you know, I'm an inquisitive guy. But I wonder how much time I've spent in rambling. I might end after this doesn't work, and then I will make a part two on like how to you know how to reduce the states. And so we have our DFS function, DFS recur, we have bounds, but there has to be something called limit of A, limit of B, bounds, and all that good stuff. You know what I mean? Like we need that. We need that because if we don't have that, we can't really do this. It's not gonna work essentially. So we need to make sure we have all the good stuff so it works. Um, that's a lot of stuff, but it's important. It's absolutely important. So we're gonna name a vector called costs. Vector reference called costs. The limit is equal to cost for 2. So once we begin, we'll say that
costs is equal to underscore costs. Right. It says uncluttered states. We don't have. Oh, we don't need to do state checks over here. So we have to also have a preprocessor directives in the game. You know, you can't work without these boys. You make life easy. I know now in modern C++, we can use stuff like constant expressions or whatever they're called. But you know, OGs is OGs for some reason. What? Says implicitly deleted default constructor of solution. I have a feeling that I knew that this was happening. I knew this was happening for a fact. I knew that this was happening. Okay. Now since we have this, what do we do? Whenever we go to a position and the position is valid, we check if okay, so we can have a an int solution. We name it, you know, it becomes max, the biggest we can ever see. And we're like if okay, so we can say that if n a is equal to limit of a, right? Limit of a and b is equal to limit of b, then what we will do is we're gonna say that the solution we have here, which is sol is equal to the minimum of sol and whatever value are coming in. Right? And at the end of the day, we're gonna return sol. What the hell is going on? Hmm. I figured this would also be happening. We have to call it. Why aren't you working? So if n of a is equal to limit of a and n of b is equal to limit of b, solution is equal to this. Hmm. Wonder why. Sake. Let's see if this works on our local. I mean, this obviously will work in the local stuff. And we're not printing anything until 1859. So why doesn't it work at all? 1859. Yeah, it works. Works with this. Um, and I'm pretty sure it works with the other, the big ass state right here. I mean, the question, the input right here. It's like right here, right here. Like, no, we don't do that over here, man. All right. So let's compile this and see. Pretty sure this will work. 3086. Yeah, yeah, this shit. This works, yeah. So what might be the problem over here, man? Public is over here. Where did we put this? Place it right before. Why is what's let's see, let's call it. Oh man, I hate it when small errors like this make you waste your time without you. Let's call it answer. Ans minimum of ans and yeah, see, it looks like it's not hitting that. Why would that not hit that? I don't get this. Hmm. Yeah, let's do something. I see. This is not going through. Okay. So so it seems to be the problem. Hmm. Okay. Anyways, let me fix this real quick. I know. All right, boys. Yeah. So, huh, that just like we predicted, leak code will TLE if you do use this. Uh, it was C++ is a very tricky language. So initially, I let limit A because equal to cost of this, and because cost had been created, limit of A was being set to 0. What should have done is initialize them right here. So order of initialization is very important. Don't forget that. But yeah, no, this is TLE in, right? We realized that we're producing too many, and so I copied the input right here. Um, and we're gonna try it on our local machine. See what's going on. Too long. Okay. Okay, this should be fun. This is really long. Let's see if our boy can crunch it up. Clear. Oh, it'll also be funny to see if we have any sort of like repeating states. Okay. Um, okay. You see, we're actually hitting states we're actually seen before. Is this only me or is it? But is this from the code or is it the ratio of the? Hmm. Wow, this is quite big. Yeah, no, I think it was rigged this. Legal rigged this. They've rigged this. They've rigged this. Yep. So yeah, there you go. This makes a lot of sense. Um, but yeah, no. So this rambling shows you, side sort of recursion states. Um, so next I'll talk about like in the next video, I'll talk about how to sort of like optimize certain states out and reduce our state space. Reducing state space can be quite tricky, but it can be done. It is done. I mean, I'm not gonna act like it's some kind of something new. But yeah, so watch out for that. All right. Thanks a lot. Peace out.